In the solar corona, each plasma particle has an incredibly high temperature, but since there are very few of them at the same time, Parker Solar Probe only has to withstand temperatures of around 1,400 degrees Celsius. This is achieved with the help of a large heat shield made of carbon foam and carbon plates, which has been given a white, particularly reflective ceramic coating to ensure the protection of other components. NASA experts have also used special materials, such as alloys and sapphire conductor tracks, whose melting points are well above the expected temperatures. In 2021, Parker Solar Probe approached the Sun to within 13 million kilometers and plunged into its corona multiple times. The record-breaking flight revealed that the surface of the corona is not uniform and smooth but characterized by local peaks and valleys. These were by no means the first findings of the mission. 2 years earlier, the data collected by Parker Solar Probe had already provided experts with some big surprises, particularly the discovery of switchbacks, short-lived, sharp bends in the solar wind's particle streams that almost reject back to the Sun. How these structures are formed remained unknown for a long time. It took another 3 years before the background to the mysterious switchbacks could be deciphered. This was made possible with the support of another spacecraft. When the Solar Orbiter, developed by ESA and NASA, made its first close flyby of the Sun in March 2022, it captured one of these striking S-shaped switchbacks on film with its special camera. The data collected allowed experts to analyze their accompanying phenomena and circumstances. It turned out that solar wind switchbacks occur where open and closed solar magnetic field lines interact. The field lines reconnect, undergoing an abrupt structural change and releasing large amounts of energy. This research puzzle, which has kept scientists guessing for over half a century, can finally be put to rest. As the data continues to arrive and scientists dig deeper into the findings from Parker Solar Probe and Solar Orbiter, it's becoming increasingly clear just how significant these discoveries are in advancing our understanding of the Sun. The ability to directly observe and measure phenomena like switchbacks, solar wind acceleration, and the peculiarities of the Sun's corona provides a treasure trove of insights that were previously only theorized. The revelations about Alfvén waves, for instance, have shed light on their pivotal role in energy transfer within the solar wind. These waves not only accelerate the solar wind but also explain its ability to maintain energy levels across vast distances. Moreover, the dual-probe approach of Parker Solar Probe and Solar Orbiter has proven to be a groundbreaking strategy. By observing the same solar wind stream at different stages of its journey, scientists can trace how energy evolves and dissipates from the Sun's corona to the far reaches of space. This coordinated effort allows experts to study the mechanisms of magnetic reconnect ion, the processes that drive energy exchange in the Sun's atmosphere, and the broader implications for space weather. Space weather, driven by the Sun's activity, is not just a topic of academic curiosity. It has real-world consequences. Solar flares, coronal mass ejections, and other phenomena influenced by solar wind can disrupt satellite operations, communication systems, and even power grids on Earth. Understanding the intricacies of the Sun's behavior helps improve our ability to predict and mitigate these effects, safeguarding technology and infrastructure that rely on stable space conditions. Looking ahead, Parker Solar Probe is poised to continue its remarkable journey deeper into the Sun's atmosphere. The upcoming close approaches scheduled for 2025 and beyond will provide even more detailed data, as the probe pushes the boundaries of what human ingenuity can achieve. Each pass brings it closer to the Sun's fiery embrace, and each transmission back to Earth carries the potential to answer questions that have lingered for decades, or to raise new ones. The legacy of Parker Solar Probe is already cemented in the annals of space exploration. Its unprecedented achievements in speed, proximity to the Sun, and the wealth of data it has provided mark it as one of the most ambitious and successful missions in NASA's history. It is a testament to the ingenuity, collaboration, and determination of scientists and engineers who dared to send a spacecraft into one of the most extreme environments imaginable. As the mission continues, it also honors the vision of Eugene Parker, whose groundbreaking theories about the solar wind laid the foundation for this endeavor. His work, once considered radical, has been vindicated in the most spectacular fashion, with the probe bearing his name uncovering the very mysteries he first proposed over 60 years ago. While the journey of Parker Solar Probe is far from over, its contributions to solar physics are already reshaping our understanding of the Sun, our solar system, and the forces that govern them. She is NASA's Icarus. Fortunately, the research probe Parker Solar Probe did not melt its wings when it recently came into close contact with the Sun again. While the spacecraft had already approached our host star to within 13 million kilometers in 2023, It's now set to break its own record by flying within 6 million kilometers of our mighty giver of warmth and life. Indeed, the data collected by Parker Solar Probe on its mission shows our star in a completely new light. But how is this even possible? How can a probe head to such a cosmic furnace without instantly burning up? And how did it manage to crack a tantalizing solar wind conundrum that has stumped experts since the 1960s? For most of us, the Christmas holidays are a time for cozy reflection. But Parker Solar Probe was to spend Christmas Eve a little differently. After all, December 24th, 2024, was a day of records for the spacecraft. On one hand, NASA announced that its Sunstriker had reached an incredible speed of around 690,000 kilometers per hour, making it faster than any other man-made object through space. On the other hand, this breakneck course had brought the probe to within 6 million kilometers of the Sun, achieving a new solar approach record. However, it would take until December 26th before NASA experts were able to give vent to their cries of joy. Specifically, there was radio silence for a day after the sensational flight, but the signal that arrived at the U.S. Space Agency on Boxing Day confirmed that Parker Solar Probe had survived its grip on the Sun unscathed and was working as desired. And so it came to pass that the probe was able to start transmitting the first telemetry data to Earth just in time for New Year's Day. In a mission update the next day, NASA announced that Parker Solar Probe's scientific instruments were also completely intact. Furthermore, the data set showed that the programmed commands from the flight computer had been successfully executed. But what groundbreaking new insights were hidden in the new data? After all, Program Manager Helen Winters of Johns Hopkins University in Baltimore emphasized that the spacecraft was making observations that no one had ever been able to make before. The somewhat sobering answer, however, is that the information collected by Parker Solar Probe is currently still a closed book. But fortunately, not because of an unforeseen transmission error. Rather, it is simply because the rest of the data will not arrive on Earth until the end of January. This will only happen once the most powerful onboard antenna is better aligned with Earth to transmit at higher rates. While the experts are currently waiting with bated breath for the results of this hot rendezvous, a glance into the future gives cause for astronomical anticipation. Parker Solar Probe is scheduled to make 2 more visits to the Sun this year, approaching our mother star on March 22nd and June 19th at roughly the same speeds and distances. Looking back in time shows the remarkable insights the probe has already provided about the Sun and how it has literally been seen in a new light ever since. How does Parker Solar Probe survive its flight to the Sun? It is no coincidence that the solar probe bears the name Parker. After all, the U.S. astrophysicist Eugene Parker attracted attention as a young man in the 1950s when he put forward a mathematical theory explaining the existence of the solar wind. In simple terms, this refers to the stream of charged particles that the Sun constantly emits into space. While Eugene Parker died in 2022 at the age of 94, he was the first person to witness the launch of a probe named after him. In fact, Parker Solar Probe had already set out into the vastness of space on August 12, 2018. But how did it come to be on its way to the Sun of all things? And why hasn't it burned up already? Regarding the mission's goal, we must not forget that there are still some big question marks surrounding the Sun. This concerns, in particular, the questions of why the solar corona is so incredibly hot, how the solar wind is generated, and what makes it so fast. While the heat scheme of celestial bodies like Earth points from the inside outwards, in other words, temperatures decrease more and more from the core to the outer layers, the Sun has a confusing second heat zone with the corona. But what causes the outer atmosphere of our host star to have a temperature of around 1 million degrees, over 200 times hotter than its surface? Since the second law of thermodynamics states that heat flow from the cooler to the warmer is impossible, the fiery corona must be based on something else, and the heat must arise within it in some way. Since experts realized they would not crack this mystery at earthly research stations, they decided to send a spacecraft directly into the solar corona with Parker Solar Probe. The fact that it did not follow in Icarus's footsteps and turn into a pile of ashes is thanks to a few exciting factors. First and foremost, there is the fact that temperature is not the same as heat in physical terms. While temperature refers to the kinetic energy of particles and measures how fast they move, heat describes the amount of energy transferred by the particles.